Hello, I'm Pete Wolf. Welcome to the MIA module titled Targeting Flood-Producing Excessive Rainfall. This module focuses on how the mesoanalyst can assist in recognizing favorable small-scale environments that can support excessive rainfall from intense convection, which can lead to flooding. This subject requires full knowledge of flood tools, techniques, conceptual models, and such. Rather than reinvent this training that already exists, a CLC element has been included as part of this training module. If you have completed the WALK Flash Flood course in recent years, you are excluded from this. If not, you are asked to first complete the Flash Flood Meteorology module in the CLC. If you're in the Western United States, you're also asked to complete the Flash Flood Meteorology in the West module in the CLC. These are fairly short modules. For more complete knowledge, you are encouraged to complete the WALK Flash Flood course in the CLC. You are also strongly encouraged to complete the Targeting Small-Scale Temporal and Spatial Threat Areas module in the MIA course before completing this module. The Targeting Flood-Producing Excessive Rainfall module essentially serves as an addendum to that one, with focus on flooding. So again, please ensure you complete the WALK Flash Flood course or the Flash Flood Meteorology module in the CLC before proceeding in this module. This is a very short module, as much of the planned content is provided in the CLC prerequisite. Here, we'll focus on how the mesoanalyst can support the IDSS and warning staff in proactively anticipating and alerting for excessive rainfall episodes that can lead to flooding. This includes understanding the key data fields for assessing the potential for excessive rainfall and how the mesoanalyst can use this data to monitor small-scale environment changes in time and space that can either enhance or minimize the excessive rainfall threat. Here is the most common process by which convection produces heavy rainfall that leads to flooding, and the process by which we typically alert people of the hazard. We start with intense convection, producing excessive rainfall rates. As this heavy rainfall persists across a given area, rainfall amounts quickly exceed flash flood guidance. Now, once this occurs, the forecaster issues a flood warning for the area. At some point thereafter, flooding is reported, although usually well after flood initiation. Through this process, however, rain has already fallen, and flooding has likely initiated prior to warning issuance. Thus, actual warning lead time prior to flood initiation is often very little, and the lead time reported is typically for flood occurrence reports, not necessarily flood initiation reports. More desirable is the ability to get the warning out as heavy rainfall gets going but before flooding initiates. Even more desirable would be the ability to accurately target a threat message an hour or two before the event occurs. These are the two areas where the mesoanalyst can benefit flood operations. How would you answer this question? True or false? Flash flood events require both high precipitation rates and sufficient precipitation periods to occur. One or the other generally will not produce sufficient rainfall amounts for flooding. Generally speaking, this is true. Consider that, at least across the eastern half of the country, neither a 3-inch per hour rainfall rate occurring for just 10 minutes or a ½ inch per hour rate occurring for an hour would be sufficient to produce a significant flooding result. We need a combination of rate and duration that yields the rapid accumulation that exceeds ground infiltration to yield flooding. Consider an example of a pulse storm environment with weak flow aloft. These slow-moving storms, albeit with high rainfall rates, generally don't last long enough to produce anything beyond ponding of water in areas with poor drainage. However, as illustrated by the red ovals on the radar animation, there can be small-scale situations in which boundary collisions could support more continuous and longer-lasting convection over a given area that could lead to small-scale flood events. As described in the flash flood modules in the CLC, the mesoanalyst focuses on two key aspects of flood-producing heavy rainfall: excessive rainfall rates and sufficient rainfall durations. Both focus on the rapid accumulation of rainfall during a short period of time that could lead to flooding. The sounding to the right shows an example of a favorable profile for high precipitation rates, including a deep, moist, above freezing layer with a narrow positive area as far as CAPE, supporting lower centroid convection and more of a warm rain process. Also, potentially a decent lifting mechanism that could be suggested by a deep veering wind profile or a strong low-level jet. Also, climatologically above normal values for key fields like precipitable water. In this example, this early November Cape Canaveral, Florida sounding has a precipitable water value a little over 2 inches, which is much above normal for the first part of November, a favorable factor for heavy rain. For lengthy rainfall periods, more than say just a 30-minute downpour from a thunderstorm, we can look for common patterns that can support excessive rainfall. As described in the flash flood modules in the CLC, these patterns include the Maddox synoptic pattern, the frontal pattern, and the mesohigh pattern. There can be other small-scale patterns that could be supportive, such as pulse storm environments with minimal flow aloft, where intense outflow boundary collisions can support longer-lived periods of intense rainfall rates. As discussed also in the CLC training, it's important to understand mesobeta element, or MBE, convective motion, also referred to as upwind propagation. We account not just for the advective vector component of motion, but also the propagation vector component as well. These components can work together to produce rapid storm or system motion, or can work against each other to generate very slow motion or even a back-building convective result. Typically, the propagation vector works to deviate storm or system motion, such as to slow the motion and deviate it from the steering flow. We typically see big supercells deviate to the right and move at a slower speed than other convection. It's also how we can observe individual storms along a line move faster than the line itself due to back building of new convection along the line. We assess MBE motion by taking the steering flow and subtracting the low-level flow, as shown in the example images at the bottom of the slide. Being able to accurately assess an imminent flood threat before the heavy rainfall happens requires accurate knowledge of MBE motion. So let's think for a moment about how the mesoanalyst can play a role during potential flood events. The key role of the mesoanalyst is to recognize the development of environmental patterns that support both high precipitation rates and sufficiently lengthy periods of heavier precipitation. This is important for yielding proactive flood threat information for Corps partners and the public, rather than reactive warning decisions based on detected rainfall that has already occurred, thus minimal lead time. So some questions that the mesoanalyst can try to answer. What are pre-existing conditions like? Is the soil moisture unusually high or low just before the potential event? Does the observed or forecast sounding support high rainfall rates? Are precipitable water and dew point values well above normal climatological values? Does the profile of atmospheric instability support deep but weaker updrafts and lower centroid storms? Does the environment support a lengthy period of heavier precipitation over a given area? Do you recognize a Maddox-type flood pattern setting up? Does the environment favor forward propagating or back building convection? What is the boundary relative storm motion vector expected to be, and what would it need to be to support excessive rainfall amounts? And will there be persistent lifting mechanisms supporting continuous convective development? Let's look at a 3-day case example from November of 2020 across the southeastern United States. You'll only be shown limited data, but let's see if it's sufficient to help pinpoint if, when, and where small-scale excessive rainfall events will occur. Okay, let's start with day 1. And this is a November day in the southeastern U.S. We're going to focus on the Florida Peninsula. And we're going to start late at night. We have a broad onshore flow pattern with high pressure to the north and a tropical cyclone moving westward over the Florida Straits. Let's take a look at some of the SPC mesoscale analysis fields and see if we can assess a higher threat area for excessive rainfall. Note that these fields change little during the period consisting of several hours before and after the hour shown. So the lower left image shows precipitable water values, which show a maximum axis over far southern Florida, with still decent values up into central Florida. However, the lower right image shows mean layer CAPE, and shows very minimal CAPE in central or northern Florida, better CAPE values to support more intense convection over southern and southeastern Florida. The next set of images shows on the lower left an upwind propagation vector, or MBE motion vector if you will. The cloud layer mean wind flow here is from east to west across southern Florida, but you see here the upwind propagation vector is in the other direction, suggesting the potential for back-building convection along bands. We also see in southern Florida very high values in the AH50 millibar moisture transport plot as well, much less further to the north. We don't see any kind of deep layer shear beyond 25 knots across the Florida peninsula. We want to see weaker shear for excessive rainfall, so that's a favorable factor. How about the lower right image showing deep moisture convergence? Here we see persistent, intense values over the southeastern part of the peninsula, around and just north of Miami. There's a second axis further to the north of West Palm Beach, although it is a bit weaker, at least suggested here. Finally, the AH50 millibar winds and dew points show dew point axes, ridges across the southeastern part and into the south central part of the Florida peninsula. Not seeing as much further to the north. We also see strong low-level easterly flow in these areas. So what do you think? Can you target the threat for excessive rainfall onto a small area, perhaps just a few counties, where the greatest probability of excessive rainfall likely exists during this period? All the ingredients shown seem to pile together right over the Miami area in far southeastern Florida. In fact, during the night, we had a nearly stationary band of heavy rain occur over a lengthy period over and just north of the Miami area, producing 8 to 12 inches of rain and significant flooding. Again, this was the area where we saw all the ingredients really come together and overlap over the same spot. There were many of the ingredients further north with a more northern band over south central Florida, and also down near the southern tip of Florida. However, these bands did not last as long as the one in the middle, and I'll show you a radar animation to show that. Our real focus is on this band here just north of Miami. And you'll see through the night the band just sits in place. It looks like it weakens a little bit at this moment here, but it then re-energizes, continuing to produce very heavy rainfall rates. The band to the north and the band that was over far southern tip of Florida either moved enough to not sit over the same location or fell apart to not produce a long period of excessive rain. Just before the event, the Miami sounding showed a favorable setup for excessive rainfall, including a deep, moist layer with narrow cape, a deep above freezing layer to support the warm rain process. We had precipitable water value of 2.5, much above climatological normal for early November. Fairly weak lapse rates and weak deep layer shear, all supportive of excessive rainfall. Let's take a look at day 2. Now at this point, the high pressure to the north is still in place. The tropical cyclone to the south is moving into the southeastern Gulf of Mexico, a little further away from the Florida peninsula. Let's see if the SPC fields can help us assess a higher threat area for excessive rainfall somewhere over the Florida peninsula. Let's start with late in the morning. First, we see on the precipitable water plot fairly uniform area of just above 2 inches of precipitable water across the entire Florida peninsula. Now, on the ML Cape field to the right, we also see a broad area of a moderate cape of 1,000 to 1,500 joules, again covering the entire Florida peninsula. Well, these are suggesting a widespread event over the entire peninsula. Let's look further. As we look at the upwind propagation vector, again this is MBE motion, the cloud layer mean wind is actually more from the southeast to northwest, so again it's in the opposite direction here, suggesting the potential for some backbuilding of new convection along a line, maintaining a line over a given location. The AH50 millibar moisture transport, not as exciting as the prior case, still decent values, but nothing highlighting any particular area. The deep layer shear is weak, as desired. How about deep moisture convergence? Throughout the morning, we don't see any real clear areas of intense moisture convergence to drive convective bands. The only exception might be just off the coast or right along the coast of far southeastern Georgia. The AH50 millibar wind and dew point plot shows multiple dew point axes or ridges in the area and a broad area of 25 to 35 knot southeasterly AH50 millibar flow. As we look at the afternoon, let's look at these plots here and see if anything changes. Again, broad areas of precipitable water and moderate CAPE values through the afternoon across the Florida Peninsula. No change to the upwind propagation vector. Seeing some increase in the 850 millibar moisture transport maybe over the southern half of Florida, but nothing really pinpointing a particular area. How about the deep moisture convergence? This is still highlighting potential area for heavier rain over far southeastern Georgia, but our focus really here is the Florida Peninsula, and I'm not seeing much here to suggest persistent excessive rain bands. In fact, we had some areas of locally heavier rainfall of 1 to 2 inches, but no areas of really excessive rainfall occurred during day 2. As we look at some of the soundings, the Miami sounding is a little bit different than in the prior case. More instability, a little bit more drier air aloft, precipitable water down to 1.9 inches. So not quite the same, a little bit steeper lapse rates. As we look a little further north at Cape Canaveral, where we have a somewhat heavier area of rainfall occur, again, we're seeing precipitable water of 1.9, some drier air aloft, a little bit larger Cape, not really like we saw in the first case. In Tampa, very similar end result here. Jacksonville, also the same, a little more moist here, 2.3 inches precipitable water, but was further away from any kind of deep moisture convergence. Now we'll look at day 3. And here we can get a sense of where the tropical cyclone is moving northward over the eastern Gulf of Mexico. So during the day, we see very high precipitable water values along the far western coast of Florida around Tampa, with slightly lower values as you go north and east. The ML Cape values are also quite substantial across the Florida Peninsula, although more marginal in values around the Tampa area over the far western part of the peninsula. As we look at the upwind propagation vector, here again the cloud layer mean wind is more south to north, and you see it opposite in direction here on the propagation vector, suggesting the potential for training bands of heavy precipitation. Notice on the 850 millibar moisture transport, a different result than day 2, with a bullseye of very high values, again over the far western part of the peninsula around the Tampa area. The 850 millibar winds and dew points show a ridge of higher dew points spreading northward towards the Tampa area during the day. As far as deep moisture convergence, once again, about the same area that just persists. So what do you think in terms of potential for heavy rain? Is it going to be over northeast Florida or southeast Florida or southwest Florida? In fact, it occurs right around the Tampa area in the far western part of the Florida Peninsula, where we have 3 to 6 inch rainfalls occur. The Tampa sounding, again, fairly favorable for low centroid, warm rain process, excessive rainfall that trains over the same area in a persistent band. The Cape Canaveral sounding further east is more unstable with further drier air aloft, not as favorable for excessive rainfall rates and over a longer duration. Now, how about that night? At this point, the tropical cyclone heads for northern Florida and is about to move inland over far northern Florida. So as we look through the late evening hours and into the night, we see once again the precipitable water values, the axis of highest values over the western part of the peninsula. The ML Cape over the peninsula is at much lower values and a little bit more favorable for what we would look at for excessive rainfall rates. However, over the northern part of the peninsula, there's an area likely due to widespread clouds and precipitation where there's minimal CAPE. That is a negative factor. So the best area in terms of what we're seeing here for heavy rainfall, heavy convective rainfall with regard to ML Cape would be again over the western part of the peninsula around Tampa and possibly far northern and far northeastern parts of Florida. Where do we have the greatest 850 millibar moisture transport? Once again, right over or just on the northern side of the Tampa area, the far western part of the peninsula, although in this case also extending into the northern part of the peninsula as well. The upwind propagation vector again is pointed in the opposite direction of the cloud layer mean wind. The pattern for 850 millibar winds and dew points has evolved more circular in nature, if you will, around the tropical cyclone circulation. So just a broader area of higher values rather than any kind of significant ridges of higher values. Maybe one that extends northward over the northern part of the peninsula, and another that sort of extends over the Tampa area down towards Lake Okeechobee. How about as far as deep moisture convergence? Where do we see, given that this is a persistent pattern throughout much of the night, where would we see the heaviest rainfall likely occur and persist? We did have some decent bands of rain over northern Florida where we see a narrow area of moisture convergence, but they moved and were not persistent over the same area. The location where all the ingredients seem to come together to support excessive rainfall rates over a longer period of time appears to be over the Tampa area and far western part of the peninsula. In this case, maybe oriented more southwest and northeast given the moisture convergence pattern. Here is the rainfall that we had during the night. Once again, a 3 to 6 inch rainfall event over the Tampa area extending towards the northeast a bit into central Florida, as was suggested by the deep moisture convergence pattern. Now, I just presented to you a simplified approach in this case example. Accurate real-time mesoscale analysis involves other data sets and additional steps such as QCing the data you're reviewing. Are the SPC mesoanalysis page data that I just showed you accurate? Nevertheless, it is interesting to observe how we might be able to provide targeted threat messaging on smaller scale flood potential just from the data shown, assuming they're relatively accurate. So in summary, as with other convective hazards, the mesoanalyst can utilize mesobeta and mesogamma or near storm environment information to target the flood threat down to a small area, sometimes down to an individual county level. In the multi-part case example in this module, the mesoanalyst could have helped the IDSS forecaster target the threat message to a smaller area in time and space. Do you see how this could support smaller scale flood watches, where targeted flood threat graphics focused on a particular county or cluster of counties, issued a few hours before a potential event? Now, this module did not go into detail about the variety of tools and technologies available to support the mesoanalyst in assessing small-scale environment changes in time and space, as this is fully covered in other modules. Keep in mind that actions like QCing the data being used and using correct conceptual models certainly apply for assessing flood potential. You have reached the learning assessment for this module. The assessment's not graded, it's simply provided for your benefit. For each question, you can pause the video as needed to come up with your answer and write it on a piece of paper. Then continue the video to reveal the answer on the next slide. Do this for each question in the assessment. Good luck.